So in this homework, I'm going to talk about the review book problems. And I'm just going to go through all of them. And even if the video gets kind of long, you can stop, pause, rewind, fast forward, whatever you have to do to get to the problems you want to see. So the video might go a little long, and try to go all the way to the end here without making a mistake. So yeah, let's get right into it. In number one, if I've got an object that's going in a circle, the speed is constant, but the velocity is changing because of the direction, and the acceleration is changing too because of the direction, but the magnitude is constant. So A is true and B is true. So number one is A and C. In number two, I've got this bucket that's at the top, and it's also at the bottom. So, and it's going around in a circle. So at the top, gravity and tension are in the same direction. At the bottom, tension goes up and gravity goes down. In both cases, we're going to say sum of the forces is equal to mv squared over r. So in number two, it's asking us, we know that the tension is 50 newtons. It's 50 newtons. We know the radius is 0.6 meters. We know the mass is 3 kilograms. So in number two, we're talking about at the bottom, we want the speed of the bucket. So at the bottom, I have the force of tension positive minus the force of gravity is mv squared over r. So I have 50 newtons minus 30 newtons equals 3 kilograms times v squared over the radius, which is 0.6 meters. So I get 20 times 0.6 over 3, take the square root of that. And so V comes out to be 2 meters per second. So that's B. And then in 3, I'm at the top. So I want the point where the tension is almost zero. Force of tension approaches 0. So sum of the forces is mv squared over r. Here they point in the same direction. So gravity plus tension is mv squared over r. For gravity, I'm putting in the 30 newtons. For tension, I'm putting in 0. The mass is 3 kilograms. Velocity is v squared, and the radius is still 6 meters. So what do I get? 30 times 0.6 divided by 3, and take the square root of that. And so V comes out to be 2.4 meters per second. And that's choice C. All right, number 4. As an object moves at a constant speed, what is its acceleration going to be? So A is equal to v squared over r. And when an object goes once in a circle, right, the distance around is going to be 2 pi r. Velocity is distance over time. So velocity is going to be 2 pi over r over the period. In this problem, it said the period was 1. So velocity is 2 pi r. So velocity squared is 4 pi squared r squared. So A is going to be 4 pi squared r squared over r. One of the r's go away. 4 pi squared r. That's choice D. In number 5, we have the wrench and the bolts. Pretty simple. The radius is 0.2 meters. The force is 20 newtons. So torque is the force that's perpendicular to the radius. You can tell from the picture that it's perpendicular already. So I just have 20 newtons times 0.2 meters. That's equal to 4 Newton meters. So 5 is choice C. Choice 6, we have this pendulum, and gravity's going straight down. And it's half a kilogram, so this is using 10 for gravity. This is like 5 newtons. And we know that this length here is 0.8 meters. But the problem is we want this perpendicular component of the force. So if this is 60, and I just draw a parallel line in, you know, this is going to be 60 also. That means this little guy is going to be 30, and that means this one is 60. So this is the adjacent side. So the perpendicular force is going to be cosine of 60. But the other way to do it is to remember that the formula is F sine theta r. Which angle is theta? It's the angle between the force and the radius. So here's the radius, here's the force. So 60 plus 30 is 150. So I could say the torque is 5 newtons times sine of 150 times the radius, which is 0.8 meters. And so this comes out to be 5 newtons times 0.5 times 0.8 meters. So this torque comes out to be 2 Newton meters. And this is choice D for number 6. So I think the hardest part about this one was trying to figure out which angle it is. But that's the idea there. So in number 7, we have this meter stick, and the meter stick, they give you the weight of it, so the force of gravity of the meter stick's 10 newtons, and then there's this force of tension right in the middle. Over here we have this force, which is 30 newtons. It's at 0.5 meters, and then we have this unknown force here that's at 0.3 meters. And you cannot solve it with some of the forces in Y, but just to show you some of the forces in Y, I'd have force of tension equals 30 newtons plus 10 newtons plus the unknown force. So I have 2 unknowns. So I have to do sum of the torques. Sum of the torques equals 0. So if I pick the center as the center of rotation, then the force of tension goes away, and so I get the torque of the 30 has to be equal to the unknown torque. So the force of the 30 times his radius is the unknown force times his radius. So 30 newtons times 0.5 meters has to be equal to F times 0.3 meters. So this force has to be 30 times 0.5 divided by 0.3. So this force comes out to be 50 newtons. So if I take 10 for gravity, the mass must be 5 kilograms. So this is number 7, and that answer was B. In number 8, I have 2-point charges, and I want to double the distance between the two. Well, the formula is mm over r squared. So if I double the distance, I'm going to get 1/4 the force. That's choice A. In number 9, if I have an object on the surface that's radius r, and I bring it out here to here, so now the radius is 2r. It's just the same thing. I'm going to have 1/4 the force. It's choice C. Then in number 10, even though I have a large planet and a small planet, Newton's third law tells us that those two forces have to be equal. So 10 is also going to be choice number C. So, problem 11. What's 11 says planet, yeah, so in 11, right, so force is Gm over r squared, right? And gravitational acceleration is Gm over r squared, right? The mass of the satellite goes away here. So they're telling us that the mass would be 1/500th. So so I'm going to take G and I'm going to divide that by 500, and then it's telling us that the radius would be 1/15 squared. So when I bring that to the top, I get 15 squared on top. So I get G times 225/500. But looking at the answers, they don't have G in there. So if you put 10 in for G, you get you can write it as 225/50. And so that's choice D. And number 12, so 12 is a Kepler's law problem, even though Kepler's law isn't part of physics 1. But as I mentioned in class before, they ask you questions about this. So if I have like a sun or something here and I have this elliptical orbit, and at its shortest point, it's at radius r, and at some other point, maybe it's at radius 2r. And what happens is when the planet is close, it's going faster. And when it's going far away, out here, it's going slower. So let's recall that work is force times distance when they're parallel to each other. And at any given moment, the velocity here, although that's a bad drawing, is perpendicular to the force. So there's no work being done, and it pops up later in one of the problems. So if there's no work being done, there has to be conservation of energy. So in other words, the total energy, E total, has to be all the potential energy plus the kinetic energy. So when it's getting further away, it actually has more potential energy. So therefore the kinetic energy has to be less. So looking at the choices, it has to be either A or B, because C and D, it's getting greater, and it's not going faster, it's going slower. So the question is the kinetic energy 1/4 or 1/2 as great? So without actually doing Kepler's law, like all this stuff here, I guess we should already know. And we should know that Gm over r squared, I'm going to set that equal to m v squared over r. So one of the m's goes away, and Gm and one of the r's goes away. So mg over r is equal to v squared, if you're still with me here. And so I'm going to put 2r into there, right? So in other words, it's like this whole thing has a half in front of it. So this v squared, it's like has a half in front of it. So the kinetic energy is equal to 1/2 mv squared. So if I put a 1/2 in front of here, that's the same thing as saying 1/2 of the kinetic energy. So the answer for this would be B, K over 2. You don't have to square it, because here there's no square on the bottom, it went away. And here's v squared, and I'm comparing it to here's v squared. So v squared in both the formulas, I don't have to square or take the square root of the 1/2. It just stays as is. All right, now 13 gets a little tricky, but in 13, a moon of Jupiter is nearly a circular orbit of radius r and a period of t. Which of the following expresses the mass of Jupiter? So I have to solve this. So again, I'm doing the G m over r squared is equal to m v squared over r. So if I go too fast, I make a mistake here. Let's just do it, the whole thing step by step. So the masses cancel out, and the velocity is going to be equal to 2 pi r over t. So velocity squared is going to be 4 pi squared r squared over t squared, right? I got to square all those things. Also, one of these r's is going to go away. So I get gm over r equals v squared. And now let's plug in all the v squared stuff. So gm over r is 4 pi squared r squared over t squared. And I got to solve this. I got to solve this for the mass. So I get the mass is equal to 4 pi squared g over t squared. Now, why am I getting r cubed here? Oh yeah, over r cubed. Is that one of the choices? Yeah, looks like that's... Four pi r cubed. Yeah, so it looks like that's choice D. 4 pi squared r cubed over gt squared. So 13 is D. Okay, in the home stretch here, 14. Two large bodies, A and B. At what distance from A along the line of the bodies would the gravitation towards the object be 0? Yikes, so this one, I don't know, I had a little bit of trouble wrapping my head around it. So A is m and B is 4m. So I probably should have drawn this one a lot bigger, but this one's a lot heavier, right? So this one's going to have a stronger force. So if I put some test mass here, right, it has to be close to him, but far away from him, right? So this, I said, came out to be D, which is R over 3. So, boy, I did a whole lot of math to show what that was, but basically I said, well, the two forces have to be equal. So this is G mm over, I said it was A times R squared, and this is G m 4m over B times R squared, like this. And when the masses canceled out here, the G's cancel out here. And so now I had to solve this for A and B. And then remember that A plus B would equal the total, my total distance R. So maybe I'll just upload the math or something. So I ended up, so if you keep going with this, right, you have m a squared r squared equals 4m b squared r squared, right? And even if you take that m's away and put a 1 up here, So you get a squared r squared times 4 is equal to b squared r squared. So a squared is b squared divided by 4, or if you go the other way, so b squared is 4a squared. So you take the square root of both sides and you get b is equal to, b has to be equal to twice a. So does that, you know what I'm saying? Like this would have to be 2 and this would have to be 1. So it's going to be 1/3 the distance. So I don't want to get too crazy with the algebra, but that's the idea with 14. So let's move on. 15. So from that kind of crazy one to a simple one here, you know, the acceleration is going to point towards the center, the force is going to point towards the center, and the velocity is going to be tangential. So 15 is B. And 16, which of the following statements for a satellite in outer space orbiting the Earth in uniform circular motion is true? There are no forces on the satellite. Well, that's not true, right? I mean, it's got to have, it would go in a straight line if there were no forces. So obviously there's a force of gravity here. Force of gravity is the only force acting on the satellite. That is true. So B is true. And C, the force of gravity is balanced by an outward force. Nope. And D, the mass of the satellite has no effect. Yeah, that's also true, right? And we can prove that because GMM over R squared is MV squared over R. It's the mass of the satellite that cancels out. You're just left with the mass of the Earth there. And the last one, in 17, an object M is traveling at a constant speed in a circular path of radius R. How much work is done by the centripetal force during 1/2 revolution? So, you know, something's traveling in a circular path. Maybe it's a mass on a string or something like that. So this is the tension pointing inwards. So again, this velocity is always going to be perpendicular to this. So if there's nothing else going on, like mass on a string is probably not the best example. If this was a planet orbiting a sun or something else where the centripetal force is definitely the only force, then the work has to be 0. There's going to be no work there because the force is always perpendicular to the motion. At any given moment, the motion is perpendicular to the force, so the work is going to be 0, right? So work is the force that's parallel to the distance. There's no component that's parallel, or you could say work is force cosine theta times the distance, and cosine of 90 is 0, so there's no work. All right, that's all 17 problems. Like I said, it's a long video, but you can just hopefully find the ones that you need help with.